Irina Sandu, and a presentation I'm in together with Florian Pappenberger from ECMWF that are, taking us to destination Earth and beyond, and next steps in global flood forecasting. So, Irina, over to you. Here.
Hello, thank you. I will just share my slides. I hope you see that.
It's perfect, thank you.
So what I'm going to talk about today, and Florian is here, ready to answer any questions you may have as well, is about a new initiative from the European Union in support of its Green Deal, Destination Earth. So, and more particularly, what I will talk about is how Destination Earth can complement efforts that are there and are happening in the community to improve, in particular, global flood forecasting, because that's what we are talking about today. So what is Destination Earth? As I was saying, it's an initiative from the European Commission aiming to develop a very high precision digital replica of the Earth, or a digital twin, to monitor and simulate natural and human activity, and to develop and test scenarios for more sustainable development and for achieving the Green Deal objectives, but also ultimately for supporting really European policy making and implementation, and reinforcing Europe's industrial and technological capabilities in advanced computing, simulation, modeling, predictive data analytics, and so on. The program is supposed to start end of this year. There are the final negotiations with the European Commission now. Is going to be coordinated by the European Weather Center, that's where we are coming from, ECMWF, the European Space Agency, and EUMETSAT, which each will have various roles, of course, in close collaborations with many partners in Europe. So ECMWF will be in charge of the digital twins, which will blend simulations and observations. I come back to this. ESA will develop a core service platform from which the twins will run, which will have a user portal, an interactive user portal to interact with the users. And EUMETSAT will take care of and handle the data lakes where all the simulation and observation data will sit. So as I was saying, the program starts end of this year. Should start end of this year. Should last until 2027. It's split in different phases, with first phase for the first 2 years, where first 2 digital twins, prototypes of digital twins, will be delivered, and then more and more this will expand towards a full digital twin of the Earth towards the end of the program, and more interactivity through the platform with the public sector users. Destination Earth, as I was hinting at the beginning, it's really about trying to complement efforts which are there in terms of science, technology, services, infrastructure. So Destination Earth will engage in continuous partnership to co-evolve its components in these areas with efforts which are there from the European Commission, different agencies, and the programs of the European Commission, as Copernicus, for example. As in the first phase, there will be 2 digital twins which will be realized building on advances in NWP science, technology, and scalability, actually, because these digital twins will bring much higher resolution. They will happen at a much higher spatial resolution, and for that to happen, it means it needs to make use of future computing architectures, and in particular of the European supercomputers, the Euro HPC facilities. So a first twin will focus on weather-induced and geophysical extremes. That's more at weather time scales, and will focus on having high spatial resolution and close to real-time decision-making support at continental scale, country, coastline, catchment scale, to respond to meteorological, hydrological, and air quality extremes. So it's really to have better predictions of extremes at this much higher spatial resolution. And the second digital twin is about climate change adaptation, and there again it's about trying to better understand the causes and explaining the feedback mechanism of change and predicting possible evolution trajectories with breakthroughs at the level reliability at regional and national levels, again through better models and higher resolution. And this is focusing on multi-decadal timescales. How will these digital twins run? Well, there will be both a continuous near real-time prediction cycle, a bit like in weather forecasting, but there will also be an on-demand service from this core platform from which the twins will be embedded, which can be both user-driven, for example, having more frequent updates or hyper resolution for certain regions or certain applications, or on demand, but event-driven, for example, if there is a storm, to have more ensemble members or high resolution over a region or both, in order to support different impact sectors. What are the breakthroughs? The main breakthroughs expected through Destination Earth are in terms of scale computing and data handling by taking advantage of the advances in extreme scale computing and data handling. It will be really focusing on having much more realistic, higher resolution models and a better combination of observations and simulations like we do today in NWP, but brought to a much bigger scale, both in terms of resolution, but also in terms of embedding the different elements of the Earth system, going beyond the atmosphere, and I'll come back to at the end. It will also realize breakthroughs in terms of trying to fully integrate policy sectors in the workflow. So basically embedding in one system, and I'll come back on the next slide to this, the Earth system and the different policy sectors from the energy, food, water, finance, and so on. And finally, it's really focusing on this open and interactive access to data, software, and workflows through this core platform, which should facilitate non-expert access and intervention. And you can read some more in various publications that went out during the last months on Destination Earth, and this is going to be shaped over the next months as it will start. So now coming to the relationship with the hydrology in particular and the flooding, where Destination Earth can complement existing efforts, it's towards going towards this full integration of the Earth system and impact sectors. So basically going from the traditional cascade of Earth system modeling, feeding something in the impact sector modeling, for example, the flood, the hydrological models, really to have this integrated modeling framework where the Earth system models and the impact sector models, in our case that we are talking about here today, the hydrology, are really in one system and with a two-way interaction. And to do this through a co-design with the users along the way, to tailor the modeling outputs to the needs of the users in the various sectors. And why is this important? What are the benefits of really having this integrated impact system, impact sector modeling? Well, think in terms of flooding. For example, the runoff, we know it's critical for flood forecasting, and this is an example. You saw some of these plots today. This is from the European Flood Alertness System, where that we run here at ECMWF. On behalf of the European Commission for the Copernicus Management Service. And you can see that we have advances in NWP. What you see in the bottom plot there allowed to forecast extreme events in terms of precipitation quite far ahead of 8 days or so ahead. And then the hydrological models, which are run using this precipitation and the output of the weather prediction models, allow to detect high probability of flooding a few days ahead of, in this case as well. This was for a case in Bosnia. But in the meantime, we know that the runoff is both uncertain, but also it's a key part of the water budget. So if you think in the what goes in an atmospheric and soil column at any point, you know, there is water coming and going out in the box in the atmosphere from the side through advection. But ultimately, what regulates the amount of water in the atmosphere and in the soil, it's basically the balance between evaporation from the soil, precipitation going in the soil, and the runoff, and what is stored in the soil itself. And now, even if there were advances in both weather forecasting and hydrological modeling, there are still uncertainties in the way we model evaporation, precipitation, and runoff. And if we bring all these components together in one modeling system, the advantage is that if we bring additional constraints to the observations we have, for example, on runoff, by constraining the runoff, and if the runoff is interactive with the atmosphere, basically, it brings constraints on evaporation and precipitation as well. So it helps us detect what's wrong in the models, in the atmospheric models, and I'll give an example of that. But there is this, to convince you of how uncertain this is, I think there's this really nice paper by Flavio Lena et al., which is a perspective which really advocates for a coordinated model development between the atmosphere, land, and hydrology community. And these plots, they show the projected change in the climate models between 2000 and 2050 and the historical period, 1950 to 2008. And basically the only thing you have to see on these plots if there are some dots and dashes or not. And you can see for temperature, there are not many dashes and dots, which show you whether there is a model agreement between the different models, or if the signal to noise ratio is smaller than 1. So if it's a measure of uncertainty, basically. And you can see that there are dots and dashes for precipitation, and there are even more for runoff, and there are even more, they're basically everywhere for runoff efficiency, which basically means how much precipitation is transformed into runoff. So given that we don't have many constraints at local or global scale on precipitation, temperature, and runoff alone, but if we have constraints on each of them, and if we bring them together, the constraints through observations on runoff, basically looking at biases in runoff, can inform us on biases in precipitation and evaporation. And I really think that pushing towards this integration between the Earth system modeling and hydrological modeling destination can help efforts in the community towards this fully integrated impact sector modeling framework. And why is this important? An example from a recent paper by Erwin Zotter, Hannah Klock, and colleagues at Reading University and ECMWF shows that there is, in the reanalysis, the ERA 5 reanalysis that many people are using, the water budget should be closed. Basically, what this plot shows you is that the P precipitation minus evaporation minus runoff, that should be close to 0. But what you can see actually that there is, it's not the red regions, it shows you that the red and here and blue, it shows you that the water budget is not closed. That's the imbalance in the water budget. And that's due to the land data assimilation in the operational forecast and reanalysis. And what that tells you is basically that the data assimilation is mainly adding snow in snowy regions and is removing water in the other regions. And the reason it does that is that because there are errors in the model. So by looking, for example, the water balance, the imbalance in the water budget, we learn that there are model errors, and we can look even more depth. And this is a plot from recent work here at ECMWF by Erwin Zotter and Gabriele Arduini and colleagues, where they looked at the impacts of better simulating the snow through a more complex scheme, which represents the snow with more layers instead of a single bulk layer. And they measured this in terms of a score in terms of the river discharge. And the only thing you have to notice here, there are some red dots and some blue dots in this top plot. And the red means that the multi-layer snow, which we know that it allows to better forecast the snow itself, it degrades the forecast of the of the river discharge. And in the blue areas, it improves on the forecast of the river discharge. And you can understand that even better if you look at these plots on the bottom, which show you the observations of the discharge peak and the surface runoff, basically. The dashed line shows the new scheme, and the full line, the blue line, shows the old scheme. And basically what you can see is that the new scheme, in terms of river discharge, it's much further, it's further from the observation. So even if it allows a better simulation of the snow, it degrades the river discharge. And digging into this and trying to understand what's happening, actually we figured out that the better representation of snow uncovers other issues with the soil temperatures, which result in and the freezing of the soil, basically, which result in water infiltrating much deeper layers, so that the discharge basically is lower. So it's exactly this evaluation with hydrological observations that allow to disentangle the sources of error in the representation of the land and the surface. So that's exactly the point I was trying to make, that bringing additional constraints on a system which is complex and not constrained enough can help you improve the models, identify ways how to improve the models and reduce the errors, and therefore improve both the atmospheric forecast but also the hydrological forecasts. So this is
Irina, I don't know
way.
how far you're there, but I mean, you have one more minute.
Yes.
Okay.
So I'm just about to wrap up. So one other thing where destinationers will help is with the spatial resolution. So this is an example of the drainage network in the existing global flooding awareness system on the left, and destinationers on the right. So they will be also going towards this much higher resolution. And ultimately, what destinationers should help with is really going towards the digital twins of the Earth system. What you see in this picture is these nice pictures our colleague here at ECMWF produced, where you see the picture on the left shows the moon, the Earth seen from the moon, from one of the Apollo missions, and on the right, what you can see is the same image produced from the ECMWF forecasts. Well, now in destination Earth, and this is just the atmosphere, right? So what we want to do, what we hope that we will achieve in destination Earth and through the core work here at ECMWF and collaborations with many partners, is to go towards this digital twin of the entire Earth system, going beyond the atmosphere, including the hydrology, including pollution, and doing this in a way that where we have uncertainty estimates, which, as you know, they are very important for both weather forecasts and hydrological forecasts. And that's all I had. Thank you.